So last time that we were together, we defined this idea of work. We said that work was force times distance. We said that a long time ago, a few days ago now, right? Yeah. We also said that work was equal to change in energy. This is a big deal right here. This whole thing had a name, the work energy theorem. It must be pretty important if it has a theorem named after it, right?
Yeah.
The work energy theorem. Work is equal to the change in energy. That's where we're going to focus today. Okay? I want to start by looking back at this. Kinetic energy is 1/2 mv squared. I'm going to write it over on the board. While I do that, I'm going to give you a ranking task to work on. Yay. Okay? I know, because you've missed them. It's been a few days. We got a bunch of them today. So here's the first one. It says, in the figures below, balls are traveling in different directions, and the balls have the same size and same shape, but different masses and are traveling at different velocities. The question asked, or the task says, to rank the kinetic energy of the balls. I'm going to let you go ahead and... So, what I'm seeing, okay, because remember, the most important part is not just the answer, but it's also, what did you say, DA? It's the why. So that's what I'm seeing most frequently. Who can defend that? Explain to me why that is indeed the case. Please.
You use math to explain more.
You're using physics.
I can explain physics.
Okay, Lauren, go.
Okay, so you have like all of them. We did.
You're fine.
Mass times the velocity squared. So we had to first find the velocity, and we did that first, and then square it, and then so how we got it.
Okay. So, like for example, for A,
yeah.
What kind of a quantity would you associate with A?
Well, so we assume that there's a 1 to B. So we have 1 square root, which is 1, and then 1 times the mass would be 2.
Wait. Okay. Slow down. I'm with you, but I'm not understanding.
Okay. So
play again.
We did the velocity to the second power.
Okay. So V squared.
Yes.
Okay.
And then we got 1 times 1 times 1.
Oh, so you're saying the velocity, the value of the velocity is 1.
Yeah.
Gotcha. Okay, I'm with you. Whew. Go ahead. Keep talking.
Okay, so then we multiplied it by the mass, which was 2.
Okay.
Then we got 2 times 1.
So you're saying that M is also 1, so but there are 2 of them, so it's going to be 2 times 1? Is that what you're saying?
Could say that. Say, like we have all those, yes.
Okay, so the number that you wrote down was 2 for that one.
Yes.
Okay, and if you wrote down a 2 for that one, what did you write down for?
Wait, but then you have to multiply it by 1/2. And then
Okay, so we're going to multiply that by 1/2.
or divide by 2,
Which would give you a number of?
1.
1, okay. Sounds good. All right, then for B, what would you write down?
The number or how we did it?
Tell me the value.
Okay, the value for that one is 4. This is divided by 2. Yeah.
So it's going to be 1/2 times, let's go ahead and write it out. Go ahead. So 1/2 times what?
2.
Okay.
And times 2 to the 25.
Is that okay with everybody? Yeah? So that's going to be 4? Okay, so is that kind of the same process that most of you took? Mm-hmm. Sweet. All right, if that's the case, there was a little bit of a dissension here between B and C. How are C and D equal? This one has 4 times the mass. How do they have the same kinetic energy?
Because the velocity is twice as much.
Go ahead.
Yeah, the velocity is double the value.
The velocity is double, but this one is 4 times.
But then you would square the velocity, so it equals 4.
Is that okay?
Mm-hmm.
Okay. That's a big important thing. If you just plug it into the equation, which is fine and legitimate, you're going to get that and it's going to come out. But I want to make sure that you're also thinking it through, like, what does that actually mean? This thing is 4 times as big as that one. They have the same kinetic energy. 4 times as big, same kinetic energy, because this one's moving twice as fast and the velocity is squared. Okay? Question?
Okay, is this what you're saying? Increasing the velocity exponentially increases the kinetic energy.
So the word exponential is really tricky because exponential growth means something very specific, and it's not this. But it increases by an exponent, right, by that squared. So it increases faster than the mass does. Or you could say that the kinetic energy increases faster than the velocity does. But I don't think I would use the word exponential here because it's not quite accurate.
Okay.
Is that fair?
Yep.
Good question. Yeah.
Is it possible for a kinetic energy to be negative because B is moving a different direction than the others?
Is it possible, Brooklyn?
No.
No? She says no. Why do you say no?
Because every time you square a negative number, you get positive.
Does that make sense?
Yeah.
Yeah. So we have a negative velocity here. But what happens to the velocity?
It's squared.
It's squared. So a negative times a negative gives you a
Positive.
positive. So is it possible to have a negative kinetic energy? It is not possible. That's an important thing. You might want to write that down just so you don't forget. Not possible to have a negative kinetic energy. Always, always positive kinetic energy.
Just sit on the floor again.
You're on the floor? Okay. Whatever works for you. All right. We're going to do another one. Before I do this one, though, I want to remind you, oops, not of that page, of the work energy theorem. The work energy theorem. Work has two definitions. What's up, yo?
Can I go to the bathroom?
You may. Work has two definitions. That's all I'm going to say. I'm going to give you another ranking task. Here it comes. You've looked at ones like this before, but not the same question. I'm going to let you know this is not a repeat. Cars are moving along a horizontal road, going to be stopped by plowing into barrel barriers. That's hard to say. All of the cars are the same size and shape, but are carrying loads with different masses. All of the cars are going to be stopped in the same distance. Rank the strength or rank the magnitude of the force that will be needed to stop the cars in the same distance. I'm going to let you think about that one for a minute by yourself, and then I will let you discuss in just a moment. But think it through.
Oh my gosh, it's the AD.
Mandalas take me 5 hours to make.
I want to see one more board. I'm waiting. It's so exciting. Oh my goodness, here it goes.
Oh, I was
Take me 5 hours. Like each one that I do.
We got
This was my one.
Wait, Arden, wrong. Wait, you said it was wrong.
I just did the math now.
You guys
Our board had the correct answer.
You did it right.
Okay, let me pause. You can put your boards down. So I'm seeing two kind of prevailing answers. B and C are bigger in both of them, and then A, D, or DA, we're not sure. Regardless, I want to know some explanations for all of it, for any of it, so somebody get started. Tommy, get us started, and then we'll add people in. Go.
So, what our group did was we knew like our givens for each of these sections is that we have the velocity and we have the mass. And with that, we found out the kinetic energy of these things. And that's where we started.
Okay, so you knew the velocity, and you knew the mass, and using those two, you could find the kinetic energy?
Yes.
Okay.
And then because of that, and we know that they get stopped by these barrels, right?
Okay.
And so the change in energy within these systems is the same as the kinetic energy because it goes from that kinetic energy, the initial, minus the final kinetic energy, which is 0. So it's just going to be the same value as the kinetic energy. And because that's the work and the distances are the same between the cars and the barrels, we knew that that would determine the magnitude of the forces.
Okay, that was a lot of stuff that just happened, and some people are like, whoa. So let's back up. That was very succinct, though. Good job.
Good job.
Let's make sure that we're all on the same page. So we all know the velocity, yes?
Yes.
We all know the mass, yes.
Yes.
We can figure out the kinetic energy
Yes.
at the beginning, right? And that, does everybody agree, is that initial kinetic energy? Kind of like when we were doing the collision stuff and momentum, we have to pay attention to beginning and end, right? Because the kinetic energy at the end is not the same as at the beginning. What is the kinetic energy at the end? 0. Why 0?
It's because they're not moving.
Not moving, velocity 0. 1/2 m times 0 has to be
0.
0, right? So this has to be 0 in all of them. Okay, so are we okay with this statement? Then the change in kinetic energy is final minus initial. Yeah, and the final is 0, so it's really the change in energy is the opposite of the initial. And that's equal to work. This is the work energy theorem.
That
Okay.
makes sense. Right?
Life is good so far. So I want somebody else to pick up there. Tommy kind of walked through it before, but walk me through from here. What do we do next? What's the next part of the step? Go ahead.
Well, since you know the masses and the velocities, you can plug in for the kinetic energy, and then once you find that,
Uh-huh.
never mind.
No, you're exactly right. That's totally
Once
fine.
you find the kinetic energy, if you put them in order, then that gives you.
That gives me the work, right? Are they asking me to rank the work?
Yeah. No. Yes. No.
The magnitude.
It says rank the strength of the magnitude of the
Forces.
Oh.
force. So I
Oh.
need something with a force in there.
Wait a second.
Well, then you know, now that you know the change in energy, then you have the work, and the work equals force times distance. But
Okay.
if the distance is the same for all of them, then you don't really need to do that, because it's like no matter what you have for the distance, it will change each of them the same. So you don't have to
Yeah.
factor that in. And so then the change in energy equals the force.
Right. The rank of the change in energies is going to be the same as the
Well,
rank
yeah.
of the forces, right?
Yeah.
I just want to make sure that we're speaking accurately because you want to be careful. If you were doing a problem like this on a test or something, like on a tiered assessment, and you just said that I ranked the kinetic energies, I couldn't give you credit for it, right? But taking this step and saying, oh, but the distances are the same, big deal. Bop, bop, bop. Huge, important deal there. Okay? So mass times velocity squared. Which one has the biggest mass times velocity squared? Like this one has the biggest mass with that one, and that one's squared, so it's going to be the biggest one?
Mm-hmm.
Yep, so that makes sense that it's the biggest. And then C
Yeah.
is the next biggest. And then there was some
Yeah.
dissension about this. What's going on here? Help me out. Which is right, which is wrong? Why do you think whatever? Go?
Well, kind of how we did it. We just plugged it into the kinetic energy formula and how we did it. So
Okay.
So if we take A for example, so we have half of 1,000
Mm-hmm.
times 6 squared,
Mm-hmm.
and then if you simplified it, it's the half of 1,000, which is 500,
Uh-huh.
and then 6 squared would be 36.
Uh-huh.
And then if you do 36 times 500, you get 18,000.
Is that okay? And then for D, what do we get for D?
D, so then you would do half of 1,600,
Uh-huh.
and then times 4 squared,
Uh-huh.
and then simplified it, that would become 800
Mhm.
times 16,
Yep.
and then that becomes 12,800.
Boom. Is that okay? So let me make sure, looking at those numbers, I'm going to agree with this one. Those of you that were saying this, can you talk to me about where that came from? Or was there just like a, yeah, go ahead.
There was just simple human error.
Simple just calculation, error in calculation?
I did GPA and I accidentally thought I had mixed up which one that you squared. Actually squared the mass.
Okay, listen to this because this is super crazy important. Say that really, really loudly. What did you mix up?
I accidentally squared the mass instead of the velocity.
Accidentally squared the mass instead of the velocity. Does it matter which one you square?
Yes.
Yes, it does. Which one are you supposed to square?
Velocity.
Okay, good for us. We okay here?
Yes.
Okay.
Time.
Yes, I am not surprised because it happens a lot, right? Somebody's going to do it, so just don't make the mistake again.
Yes.
Okay? All right. One more of these, and then we're going to move on to something new and a little different. Here you go. Cars are moving along horizontal road are going to be stopped with plowing into identical barriers. All the cars are the same size and shape, but they are carrying different loads with different masses. All of the cars are going to be stopped by the same constant force by the barrier. Rank the distance that will be needed to stop the cars with the same force. I'll give you a moment to work on this by yourself, and then I'll let you discuss. Go. Unless you got it wrong before. Why do you not need to erase your boards to answer this question?
Same thing.
Is it the same problem?
No, but it's same like
Almost the same.
It's the same concept, the same result. So what was it? B, C, A, D? Is that what we decided? So if you, for example, I'm not saying this would happen, but let's say that you were given this question on a test, and then you were given this question on a test. Would it be a legitimate answer to say C above?
No, you have to give a reason.
That's never a good answer.
You have to give.
It's honestly never a good answer, but especially in this case because it's not the same question, right?
Yeah.
So talk me through your reason for this answer this time. I want new people. I've talked to all four of you. I want new hands up.
Open it about this.
New hands up. All right, I'm going to start calling on people, but I'll give you 30 seconds to talk to your table mates. Go. I'm going to pick on, who am I going to pick on first? I'm not going to pick on you. Sorry. Can I pick on you a little bit, Peyton? Just start us. You don't have to tell us everything. Just get us started.
So you need to find this kinetic energy,
Uh-huh.
which you're going to take, basically, like, you're going to take the velocity and square it,
Mm-hmm.
and then you're going to multiply it by the mass and then divide it by 2.
Uh-huh.
And then after that, you're going to take that answer and subtract 0 from it to get the change in energy.
Awesome.
Which is, and then since the forces are the same,
Uh-huh.
because you're going to do work divided by force, which all the forces are the same, so the distance is really just the energy.
High five for you. Woo! That was great, wasn't it? Yeah, nice job. All right. Is that making sense to people? That was brilliant. That was very good. So the works are going to be the same, or the works are going to be this, the force are going to be the same, so distance is going to be in the same ratio as the work. Is that okay? All right. So the next thing that I'm going to show you is another way to think about this process and another way to think about the work energy theorem, okay? It's something that's called a bar chart. So you may want to put a line in your notes and just write down a couple things here about bar charts. I will tell you that when I first was introduced to bar charts, it was about 5 years ago. And it was from these physics education gurus that were like, this is the next big thing, it's so important, blah, blah, blah. Whoa, right? And I listened to them, I listened and I was like, those are so dumb. My students are so smart, they don't need this. Like, why would I waste my time teaching them this? Because they got it, they can do it. What's the point? So I ignored them. Like, I ignored this whole, bar chart movement for, 4 years. And then I kind of, listened, but I kind of, half listened. I'm sure you don't know anything about that, right? Ever, just half listening to people?
I do.
Right? I know. But then I was I gave them a little bit more time. And I have come around and I have realized, especially, so for you guys, yes, but especially for my AP Physics kids, you always think AP Physics, that's got to be hard, right? It is hard, but it's very conceptual, and these bar charts make all the difference in the world. So I am a bar chart convert. I love them now. So I want to teach them to you, but the reason I tell you that story first is because I don't want you to turn your brains off when I start. Does that make sense? I don't want you to be oh my God, that's so easy. Why am I wasting my time with this, right? I went through that process for you. Okay? So just trust me for a couple minutes. It will be okay. Deal?
Deal.
Deal. All right, here we go. So here's what a work energy bar chart looks like. So we're going to do one together, and then I'll let you do one by yourself. Sound good?
Yep.
Okay, so bar charts. The idea, you guys have done like bar charts or histograms before in classes, right? So like each little like part of the bar means something. Yes?
Yep.
Yeah, this is not a new concept to you. So here's the deal. It says the velocity of a tugboat increases from 2 meters per second to 4 meters per second in the same direction, while a force is applied to the tugboat for 20 seconds. Does that seem reasonable enough? Okay. It says complete the work and kinetic energy bar chart for this process. The bar heights should be correct and in correct proportion to one another. So here's the situation. At the beginning, does the tugboat have kinetic energy?
Yes.
Yes.
Yes. At the end, does the tugboat have kinetic energy?
Yes.
Yes.
Does it have the same amount of kinetic energy?
No.
No.
No. Because the amount of energy has changed, what does that mean has been done to the tugboat? Work. Does that make sense to everybody? Okay. So we've been writing, and this is the part I want you to write down because this is kind of important. We've been writing work is equal to the change in energy, or we could say energy final minus energy initial. That's what we've been saying. But we could also write it as the final energy is equal to, if I add my initial energy on both sides, is that okay, algebra-wise? Add it to both sides. My final energy, EF, is equal to the initial energy plus some work that's done. So the total amount of energy I have is the initial part plus anything I put in. Okay. They quantified the total at the beginning, the initial, as 2 bars of energy. Okay. I need to figure out how much work was done, and I need to figure out how much energy we have at the end. Okay. Am I going to have more bars or fewer bars at the end than I did at the beginning?
More.
More? Okay. I would like you to talk to your table mates right now and see. I don't want you to do everything. I want you to see if you can figure out how many bars I need to have in this column here. Talk to your table mates. I'm just going to give you a minute or so to talk. Go. See if you can figure it out.
You said 3, 2, 1, and I had to write it quickly, and you know what?
And you got stressed out?
I'm not liking this judgment that I'm getting.
We got 4.
No, you didn't.
Yeah, we did.
Do you condone that erasing that's happening there?
Yeah. We got 4.
All right. I see apparently a lot of 4s, more 4s than were before, and an 8. Talk to me.
We'll figure it out.
Okay, you can put your boards down. Let's talk about it. Let's talk about it. I don't want to tell you how to do this. I want you to tell me how we might be able to figure this out.
I need to defend my number.
You need to defend your number. Were you the only one at your table that thought that number was right? Did you have support?
We had no clue. But, well, we had a clue. But, like, we just all kind of were like, that sounds about right. So.
Okay. Defend your hunch.
Okay, so it's the velocity is twice as large as the original velocity, so we thought that the kinetic energy would be 4 times as much. Because the thing
Arbitrary choice? Like, where'd you get that
No,
from?
because the thing that we were talking about where it was like, if the mass doubles, then it's some velocity. I can't explain it, but like.
Yes, you can. Keep talking.
English doesn't work for me.
Yes, it does.
So like, if you have the original velocity and it's 2, and then it's twice as much, and then it would be 4. Well, then the kinetic energy would be 4 times as much because the mass isn't changing, but you still have to square it. It's just.
Lauren seems convinced. Like, I'm just watching her face.
4 times as
I
much,
did
then
some
it would
math
be.
and it looked pretty. It's convincing.
It looked pretty right.
If it's 2 times, if it's squared, so then the original, it would be 2 squared, so then that would be 4. And then the other one would be 16.
Yeah.
And, yeah, 16 divided by 4 is 4. So then it would be 4 times as much. And 2 times 4 is 8.
Okay.
So I'm defending my number.
I can deal with that.
Okay, so I think what I'm writing down is what you're saying.
Yeah.
So 1/2 m times 2 squared is 1/2 m times 4. Everybody okay with that?
Yeah.
Yeah.
Okay. 1/2 m times 4 squared is 1/2 m times 16.
Yeah.
And this, is this one twice as big as that?
Yeah.
No, it's 4 times.
It's 4 times as big as that. Is that okay?
Yeah.
So if there are 2 bars here,
There should be.
Alex, how many bars should there be over here?
8.
There should be 8 bars over here.
Yeah.
Good job.
We originally had 8.
I know, and then you changed your answer. Peer pressure or something.
Yourselves.
Because Carolee, she's like, okay, write a dash 2 equals 4.
1, 2,
Told me to
3,
write a
4,
dash
5,
2,
6,
which
7.
I assumed would equal 4.
8.
Okay. Is that okay? Now, we're not quite done. If we have 2 bars of energy to start, and we end up with 8 bars of energy, how much work must have been done?
4.
6.
More.
There are 8 here, there are 2 here. Remember we said... Yes, it was a weird noise. That initial kinetic energy plus work has to equal final kinetic energy.
6.
2 plus what equals 8?
6.
Okay.
Yay!
It would be 4 though. We just write it down as 4.
You could be wrong.
6.
Which will make us feel better about it.
Yeah, we know it's 6, but can we just say for now it's 4? Oh.
No. Doesn't make any sense. All right, are you okay here? Yes? Okay. My last, no, never mind, I can't ask that question. Doesn't matter. All right, we good?
Yeah.
Now that you know how to do it, I'm going to give you another one. Wait, that wasn't the noise you're supposed to make. Let me try it again.
Yay!
Wait for it, wait for
Sorry,
it.
I'm really loud today.
Wait.
Now that you know how to do it, I'm going to give you another one.
Yay!
Woo!
All right.
Enthusiasm.
It sounds like boo.
I want you to work on this by yourself first.
Oh, I like those.
Okay, so I'm seeing some small numbers, I'm seeing some large numbers. Those of you that have large numbers, where are you getting those numbers from? Those ginormous numbers. Go, Aoife, what you got?
Okay, so alright, so for the picture, basically what we did is we plugged in the numbers for the kinetic energy.
Mm-hmm.
So we plugged in so it ended up being 1/2
Mhm.
times 4 times 2
Mm-hmm.
times 4 squared.
Mm-hmm.
And so then that ended up being 1. So that was 16.
Mm-hmm.
And then for the
And then you kind of, yeah.
we did the exact same thing, and then we found a difference.
Okay. So that's the initial one, and then the final one was what, 36 or something like that? Yeah. So you can draw lots and lots and lots of boxes, but that sounds like a lot of work. And just coloring in pretty things, that's fine, but sometimes I actually want you to draw the rectangles. So some of you over here decided to make your life a little bit easier, right? Yeah. So kinetic energy was 16 initially, and 36 finally, which means that the work was how much?
20.
20. So you could either draw 36 boxes here, or you could see that these things have something in common. What do they have in common? Like a 4?
Yeah.
Right? You can divide by 4 on all of them. So you could just do
4, 5, 9.
4 boxes here, 5 boxes here, and 9 boxes here, and do you see how those still add up? Right? So you do like 1, 2, 3, 4, whoop, whoop, and then 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, like so. No? Is that making sense?
Which one is like more correct?
Generally, when you see bar charts, they will be down to their most common denominator. They will be simplified. That's not incorrect, however. You could have divided by 2, and that would still be right. You could have multiplied by 100, and that would still be right. Right? It's all ratios. But the simplified version is usually what you'll see. Yeah?
Will this be like on a test?
Sure.
Okay, and if this were to be on a test,
For example.
Would you rather have it simplified, or do you still just not matter?
I wouldn't count it wrong, regardless. Does that make sense? Yeah. Okay. I promised you that before the end of the day, we would define gravitational potential energy, and we've got 4 minutes. So, erase your boards, stay right there, don't go anywhere. We're going to define it real quick. Here it comes. Gravitational potential energy
I just like.
Francis, if you need to move so that you're not talking. Thank you. Gravitational potential energy. We said potential energy was the energy that's stored, right? Another way to talk about energy is energy due to position. Energy due to position, dealing with gravity, okay? We have talked about gravitational potential energy, you just didn't realize it before. When I lift the frog from here to here, am I doing work?
Yes.
I am, indeed I am doing work when I lift the frog from here to here. At this moment right here, how much kinetic energy does he have?
0.
At this moment right here, how much kinetic energy does he have? 0. So even though work, which equals the change in energy, we got 0 here, we got 0 here, but something must have changed if I have indeed done some work. And the thing that has changed is his gravitational potential energy, or his potential energy due to the position away from the Earth. Okay? So we take that, and we also know that work is force times distance, where the force and the distance are parallel. Okay? If I am moving the frog, the minimum force that I'm going to have to apply to get him from here to here is equal to his weight. Does that make sense?
Yeah.
We've talked about that a couple times, like when we were walking up the steps. The minimum force I'm going to have to apply is his weight, and his weight is calculated by using m times g, right? That's the force of gravity, his weight. Okay? D is the distance that he's traveling, but let me ask a question. Am I doing work right now?
Yes.
Yes. Am I doing work right now?
No.
No. So that distance has to be a very specific kind of distance. And if I'm talking about gravitational potential energy, it's always going to be in this up and down direction. Does that make sense? Yes. Relative to the Earth. So usually instead of saying D, we will write height. H for height. Okay? So the mass of the frog times the acceleration due to gravity, this is the 9.81, or 9.8 meters per second squared, times the height, gives you the value, if we set something else equal to 0, for the energy, the potential energy gravitational. Yeah.
This is in the book.
It was in the book.
Yes.
Woo! Well, that's good. I didn't need to tell you then, huh? So I hope you read the book. I hope you do some calculations in the book, because we do have a quiz that involves that next time. It's not hard, but if you don't do your homework, you'll probably be a sad kid. I hope you have a wonderful day. I'll see you on Wednesday. Thanks, yo.